Yeah, my name is Dylan Hickson. I'm a postdoc in the Planetary Radar Science Group at the Arecibo Observatory. And as the title of my talk suggests, today I'll be talking to you about how we can use the polarimetry from our radar measurements to study the surfaces of radar-observed asteroids. So as you know, planetary radar is critical to post-discovery characterization of near-Earth asteroids. Radar imaging, such as this sequence of delayed Doppler images of NEA 1998 OR2 obtained last year, provide meter-scale resolutions comparable to that of spacecraft flybys. In these images, you can actually see not only the shape of the object, but also what looks to be a possible crater on the leading edge over here. The radar echo that we received is sensitive to the wavelength scale or centimeter scale physical properties of these surfaces. And in particular, the polarization of the scattered signal depends on the scattering mechanism that occurs, which is directly related to the physical properties on that surface. So we can take the measurements of polarimetry from our radar observations and relate that to the physical properties through radar scattering theory. One of the most common metrics used to do this is the circular polarization ratio, or CPR, which is essentially just a ratio of the power that's received in two orthogonal circular polarizations. So planetary radar systems transmit a circular polarization and then receive in the orthogonal left and right-handed circular polarizations that are often termed same sense as that transmitted or opposite sense to that transmitted, where the ratio of these two is the CPR. And the CPR has been shown to be sensitive to a variety of properties on the surface, such as ice content, surface roughness, particle abundance, distribution, and morphology, and the composition in the surface. So the convolution of all of these various factors influencing the CPR makes physical interpretations of these measurements difficult and oftentimes ambiguous, as was recently exemplified for Bennu, where pre-OSIRIS-REx radar observations measured a very low CPR that was interpreted as Bennu having a very smooth surface, largely devoid of boulders, which is in stark contrast to the spacecraft imagery provided by OSIRIS-REx. So this research that I'm discussing today was motivated by a need to apply additional constraints to these physical interpretations to augment just a single metric such as the CPR, and in particular, looking at other polarization states outside of just circular polarization to do this. So in order to measure the polarization state of our radar echoes, we have to construct the Stokes vector from the received signal. So here the Stokes vector is a 4-element vector with parameters labeled from 1 to 4 here, and we can construct those based on the complex voltages measured in both the right and left circularly polarized receiver channels. On the bottom right here, I'm just showing a block diagram that kind of outlines how these measurements are calibrated and then processed to derive images of Stokes parameters, and then ultimately polarimetric parameters that I'll describe over here in a bit more detail. So the first Stokes parameter is just the total power in the received signal. The fourth Stokes parameter, and based on these equations here, gives information on the circularly polarized component. And then the second and third Stokes parameters give information on the linearly polarized component of the signal. And then you can use these Stokes parameters to construct these variables over here, such as the CPR, which you can get from the first and fourth Stokes parameter, and then the degree of polarization, which is just showing what fraction of that signal is polarized as opposed to unpolarized or randomly polarized. Similarly, the degree of linear polarization just looks at the second and third Stokes parameter and determines what fraction of that radar signal is linearly polarized. And last, in our work, we consider the MCHI decomposition, which is a false color RGB image that is created from a somewhat complicated combination of the Stokes parameters that I don't have time to get into, but it was developed in Rainey et al. 2012 for mini-RF synthetic aperture radar observations of the moon. Mini-RF is a dual-pole radar system similar to Arecibo that transmits in one polarization and then receives an orthogonal polarization. So the same technique can be applied to Arecibo observations. And I just want to quickly give the glaze over of what the interpretation for these images would be. Blue colors show an increase in the opposite sense radar power. Red colors give an indication for the same sense radar power. And green colors give an indication for the randomly polarized power, or essentially 1 minus the degree of polarization that I introduced earlier. So for the work I'm discussing today, we looked at archival radar observations of 3 near-Earth asteroids, 1999 JM8, Bennu and 1998 WT24. So we first created delayed Doppler images of each Stokes parameter, following the method I described in the previous slide, and then used those images of Stokes parameter to create delayed Doppler images of the various polarimetric parameters. We also carried out numerical simulations of the M-chi decomposition for irregular particles to provide context for these images and observations of asteroids. Since the M-chi decomposition was originally developed for the moon, which generally has smoother surfaces than what we've seen for spacecraft visited asteroids, we wanted to augment the interpretation based on a more complex geometry. So that's not discussed today, but it is discussed in a paper that I'll provide a link to at the end of this talk. And then ultimately, what we want to know is what is the physical interpretation that we can pull out of these polarimetric images? And so I'll discuss that a little bit as well. So first up, here are the results that we have for asteroid 1999 JM8 that was observed at Arecibo in August of 1999. So this first column here, you're seeing total power images on 3 days of observation. And immediately you can see that we're observing different rotation phases due to this roughly 7-day rotation of this asteroid. And you can see various surface features such as these possible concavities, which could be potential craters, as well as these prominent ridges here in the data on August 3rd. And then you have the delayed Doppler images that have been created for the various parameters, circular polarization ratio, degree of linear polarization, degree of polarization, and M-chi decomposition. So just a few highlights here. The CPR measured for this object is very low, and these areas of concentrated very low CPR indicate that there's possible specular scattering that's going on, which would have an increase in the opposite sense radar power. And that's mirrored here in the degree of polarization images, where we have specular scattering resulting in very highly polarized radar echoes. So these regions of high polarization in the radar echo match very well with the regions of low circular polarization. There's very little linear polarization measured across this object. However, the values are still non-zero. And what's particularly important is that the values increase as we go from the leading edge here at the top of the asteroid down to the trailing edge, where the geometry of the observation is such that the incidence angle is increasing from this leading edge to trailing edge. And based on work in radar polarimetry on Venus and the Moon, this is an indication of subsurface scattering occurring, which could hint at a possible regolith on this object. And then the M-chi decomposition here is showing mostly blue and green colors, which show some depolarization is occurring as well as that OC power. And these results for circular and linear polarizations are consistent with past work on this object. When we analyzed Bennu, we did something slightly different, where we averaged all radar data over roughly half of a rotation phase of rotation in Bennu. And what this did was averaged all those radar scans so that we look at the average radar scattering properties across the surface as opposed to analyzing one specific orientation. And what we see is very low CPR, similar to the disk-integrated CPR value that was used as that interpretation that I introduced at the very beginning of this talk. And similarly, very low linear polarizations, although I should note that these are non-zero values. The M-chi decomposition shows blue and green colors very similar to 1999 JM8, although that interpretation that there could be a regolith on the surface is not necessarily applicable to Bennu, given that we know how many boulders are on the surface from OSIRIS-REx spacecraft imagery. And then the degree of polarization images show at this leading edge, where we have that incidence angle near zero, the return is highly polarized, but as we move at higher incidence angles, the radar echo is more and more depolarized, roughly 40% depolarization across the surface, which indicates that there is some diffuse scattering occurring. 1998 WT24, which is an E-type asteroid, which are among those with the highest radar measured circular polarization ratios, has a very different polarimetry kind of landscape here. So the CPR is really high. This color bar is going up to 1.5 in this case. And here we're showing two views of the asteroid. One averaged over 20 degrees of rotation and one averaged over 200 degrees of rotation. And so this is showing roughly one orientation, whereas this is showing the average surface properties. And the CPR is consistent between the two. So we know that the CPR is high on average over the surface, whereas the linear polarization, which is high in this one orientation, kind of gets averaged out when we are averaging radar scans over more degrees of rotation. And based on our understanding of this subsurface scattering effect on Venus, Moon, and the Earth, this is consistent with the interpretation of a regolith on the surface of this body. The degree of polarization, similarly, is very highly depolarized when averaged over more rotation, and we have more highly polarized radar echoes for this specific orientation. And then the MCHI decomposition results are just vastly different from 1999 JM8 and Bennu, with green colors dominating and also seeing some red colors in there, which we don't see for Bennu or JM8. So we can quantitatively compare the results for these three different asteroids by taking those two-dimensional delayed Doppler images and mapping them into one-dimensional histograms, and then fitting those histograms with probability density functions, where we can look at what are the essentially modes of those distributions. So what is the I guess you could average values across the surface for these various images, as well as what is the variance in the distribution. So that's reflecting not only the error in the measurement of these polarimetric parameters, but also the variation across the surface as we're averaging radar data taken over various amounts of rotation of the object. So based on the kind of qualitative understanding of those images and working through that quantitative analysis, which I don't have time to get into, I'm just briefly going to go over the physical interpretation that we concluded based on our work. So 1999 JM8 is likely blanketed by an appreciable regolith layer, although we can't rule out the possibility of irregular boulders on the surface similar to Bennu. 40% of the radar echoes from Bennu are depolarized, which shows some diffuse scattering occurring, which is contrasted by the low CPR, where typically a high CPR is associated with diffuse scattering. The non-zero linear polarization, so the small amount of linear polarization on Bennu, likely isn't resulting from a regolith layer, similar to what we interpret for JM8, and could possibly be resulting from the boulders on the surface themselves. And then we know that since the polarimetry of Bennu is homogeneous across those images, surface scatterers must dominate the radar echo of Bennu. WT24 has in thermal data, a low thermal inertia, as well as a strong optical opposition effect measured for E-type asteroids, which indicate that there could be a regolith on the surface, which is consistent with our measurement of linear polarization in the radar data. However, the CPR and MCHI decomposition require a dense or rough surface to consolidate that high CPR that was measured. So to reconcile these kind of two characteristics, we propose that this object has a thin regolith mantling a rugged, dense interior core. That core could be solid rock or a mixture of rock and regolith or ice, where the coherent backscatter opposition effect could be contributing to that really high CPR that we measure. Although ice retention on small near-Earth asteroids seems unlikely, recent thermal modeling has shown that it's not impossible in all cases. So doing this kind of radar polarimetry for E-type asteroids could be an interesting way to try and understand more of their physical properties. So just to summarize, we can increase the accuracy of our physical interpretation from radar data by expanding the polarimetric techniques that we use to analyze that data. And not only can this be done for future observing campaigns that make use of an improved calibration scheme, but we can also look back at the archive of hundreds of radar data for hundreds of asteroids that have been observed, and then apply this technique to reanalyze that data. And these future observing campaigns could be applicable to the new radar facilities that will be necessary to keep up with the increase in near-Earth asteroid discoveries from new NEA observing programs, such as the possible radar on the Green Bank telescope or potential new telescope at the Arecibo site. And so I'll end there with just showing here, you can look at this research in a bit more detail in our publication that's currently kind of in the final stages of publication in the Planetary Science Journal. And I'd like to thank all the staff at Arecibo and University of Central Florida, as well as our collaborators for making this research possible. All right, thanks for listening.
Great, thank you very much, Dylan. That was really interesting. We're right around the 15 minutes again, so I'll suggest that you stop sharing and we can start setting up the next presentation as anyone types questions that they have into the chat. And it looks like we have a question from Carrie Nugent. Great talk. Are you going to expand this study to more asteroids? If so, which ones?
Yeah, that's a great question. So absolutely, the next step is to try and build up a statistical sample for these properties, similar to the Benner et al. 2008 study that looked at how the CPR was actually correlated with taxonomic class for asteroids. So we want to look at that for linear polarizations, the MCHI decomposition. Which asteroids we look at is strictly related to the signal-to-noise ratio. To extract the linear polarization, we need a really high SNR, so that will kind of limit which objects we can do this analysis for.